I think we'll go ahead and get started today and welcome everyone to our distinguished lecture series. It's really my great pleasure today to introduce our speaker today, Dr. Susan Brantley, Distinguished Professor and the Barnes Professor of Geoscience at Pennsylvania State University. Sue's an extraordinary geoscientist whose research centers around broadly interactions between water and rocks. She has a particular interest in the critical zone, that top of vegetation to groundwater, and evaluating questions that concern chemical weathering and rates, and with and without microorganisms. Really, she was one of the primary mover and shakers in the National Sciences Foundation's Critical Zone Observatory program, PI of the Shell Hills CZO that has produced just an extraordinary amount of understanding and to near surface processes. Sue's the recipient of a very, very long list of awards and memberships. I could spend all day going through the list, won't. But she is a member of the National Academy of Sciences, and that probably says it all. Without any further ado, I'm going to turn the time to her. She's going to speak to us today on subsurface landscapes of oxidation and reaction in the critical zone. So, Sue, thank you very much.
Thanks, Kip. I'm real happy to be able to give this talk. And it is too bad that I can't be in Utah, especially because this big storm we're having in the East Coast is we're getting it rain out here. And as a skier who always wanted to ski backcountry with Kip out where you guys are, it's just too bad to be giving a talk from rainy Pennsylvania, in my office, in my home, to a lovely place like Utah. But I'm happy to be able to talk about some work that we've been doing. I'm going to talk about what we've been learning about weathering and the subsurface. And the talk is co-authored by a lot of different people, but I wanted to highlight Jin Gu, who did much of the, heavy lifting. And then also at the end, I'll talk how we've been using Seismic to understand some of this. And that part of it I did at least partly with my husband, Andy Nyblade. So what I've been interested in for a really long time is what controls the thickness and distribution of soil across the surface of the earth. And this is a beautiful picture from Plinlimmon showing shale. And shale is really the most common rock type exposed in the critical zone. And so a lot of my talk will be about shale examples and the Critical Zone Observatory where we worked in Pennsylvania. So, well, why are we interested in this? Why would anybody be interested in this? And I like this figure, which is from a paper in, I guess, 2009. And it really is about the importance of understanding groundwater flow and how we can model groundwater flow, and what the black box nature is of a lot of the models. So this is just 3 different schematics of different kinds of models used to understand water flow in the subsurface. And in some cases the model just assumes that everything below the soil or the land surface is homogeneous. In other cases there may be an impermeable boundary and then a permeable layer at the top, and then in other cases maybe there's more than one layer. But the point of this is that we're often making ad hoc assumptions about these layers. And then this is what controls the groundwater flow. And when we drink groundwater, it controls a really important water resource. And what I believe is that much of the flow in the subsurface is either controlling the weathering, or the weathering is controlling the flow. And that the more we can understand about the weathering and how it layers out in the subsurface beneath us, the better we'll be able to understand about this water resource. So it's kind of a question of, can we predict the distribution of these sort of subsurface weathering? Not so much can I predict where there's shale or sandstone in the subsurface, but what did the weathering do to that underlying rock? And where are the weathered zones and the unweathered zones? So we've been exploring this using straight up geochemical tools. That's what I've mostly done. But most recently, as I mentioned, I've been working with my husband, Andy Nyblade, and students here at Penn State to try to actually take seismic data, and I'll talk a little bit about this at the end, and then a rock physics model with Gary Mavko to be able to actually predict porosity and relate that to where the weathering is so that we can start to see weathering in 3D. So I'll talk about that. So some of what I do has been based in models, and I'm non-modeler. I work with Marina Lebdeva, and the state of the art now with reactive transport models is actually quite advanced. For those of you that model and are interested in the equations, this is a sort of a 1D set of equations. What we normally do is set up thought experiments and then run numerical models about the thought experiments. So instead of modeling a very specific system, we typically, are looking at how water rock interacts for very simplistic systems. And, our favorite that we've done a lot of models for, that Marina's written the models for, is simply quartz plus albite going to quartz plus kaolinite. So it's sort of like the simplest granite type rock that you might imagine. The quartz is in there so that it stays isovolumetric, so the weathering is isovolumetric. And then the albite is dissolving, albite being the most common mineral in the surface of the earth, and forming kaolinite. So we use a form of the advection diffusion expression. We have an expression for the dissolution. So here's the albite going to kaolinite plus solutes. And then we have rate constants and rate equations. And there's always a rate constant in the surface area of the mineral. So we use these models to explore what types of behaviors and what kind of patterns that we expect. And then we have been able to look and find these often at the Earth's surface. So what we'd like to be able to understand, as I've sort of been alluding to, is sort of the subsurface landscape. So in 3D, we're very far from really being able to do that, but we're kind of starting to get there. And then we'd also like to be able to predict them around the surface. So one of the ways that we convinced the National Science Foundation to fund the National Critical Zone Observatory Program was to say that we would explore different kinds of environmental variables and how these variables controlled some of these processes like weathering. And so this was just a diagram that we, at one point we're arguing, we need to understand time, lithology, how all these different variables. And the one that I'm going to talk about today is erosion rate. So that'll be the one that I focus on here. So the outline of how I'm going to talk about this is I'm going to first just talk a little bit about reactive transport. I call this a primer. It's not really a primer because I'm really going to talk about the equations as much as what they tell you about the system. Then I'll talk about weathering at Shell Hills, which is the Critical Zone Observatory where I work, which is just real close to here in central Pennsylvania on shale. And then I'll look at erosion and weathering. This will all be kind of in 1D. And then I'll start to say, like, what do we expect in 2D or in 3D, and then I'll conclude the talk. So thinking about things in 1D are the easiest for me. The weathered, unweathered interface is easiest to think of, at least I think, at ridges developed on one rock type, so you make it as simple as possible. And if you have more precipitation coming in than you're losing as evapotranspiration, then you can think of net downward water flow. Of course, it's not all that happens, but like we're kind of simplifying the system just to be able to think about it. So as rock material is brought to the surface and exhumed in this sort of 1D world, water is going to be moving downward, and it is charged with oxygen and CO2, which are the two most important reactants other than water itself, flowing downward, generally dissolving soluble minerals. So I'm going to talk quite a bit about pyrite. So we're going to talk about oxidation of pyrite, and that's what this reaction is. But then the CO2 water, the carbonic acid system, is going to dissolve all the minerals that have the base cation oxides. So this is kind of geeky the way I wrote this. This is just written as the component magnesium oxide. I'm not trying to talk about, you know, this particular mineral, but any mineral that has base cation oxides is going to dissolve in the acid water and go into solution. So that's what's happening sort of simplistically when you think about this downward arrow. Now, if this landscape or rid is sitting at the surface for a very long period of time, and if there's erosion happening at the surface, so you would expect the soil thickness to decrease with time in that case. But what we actually see is in many locations, soil thicknesses can be maintained for very long periods of time, for geologically long periods of time. And so the only way that can be happening if there's erosion at the surface is that this interface here is also moving downward. So there's a weathering advance down here that allows material to turn it into soil. So if you think of standing up here for a geologically long period of time while erosion is happening, if this soil stays constant in thickness and over time, then material is actually coming from the rock down here and moving up, weathering through the system. So at the same time that water is moving through at a very fast rate, at a slow geological rate, material here is moving through the system, weathering and being taken away in this sort of 1D system. So how does this happen? Well, fractures are opening, blocks or particles are forming down here. They move up into this weathering zone, and as they dissolve and crack further, they get smaller and smaller until they are exhumed at the surface and exposed as soil. So in an ideal system, and I've kind of written papers about an ideal hill, since I'm trained as a chemist, you know, you think about the ideal gas law. The ideal gas law isn't true, but it's a very helpful formulation to think about. In an ideal hill in this 1D, you know, sort of ideal ridge, in a geomorphological steady state, the erosion rate would equal this weathering advance rate, and this soil thickness could stay constant with time. And we know at some level this is true. Systems are always going to be perturbed away from the perfect steady state, but we think that there are feedbacks that are connecting so that the erosion rate and weathering advance rate are tending to move to be more or less equal any place that we have a thick soil that's maintained constant over geologically long time periods. And one of the things that people are really interested in are what are these feedbacks? I think some of the feedbacks are solution chemistry, soil gas chemistry, and then particle size and you know, sort of fracturing kind of controls that can allow erosion rate and weathering advance rate to couple. But that is how we're going to think about this, as if it could be at a steady state. So if you run these really simple, well, they're not that simple models, but if you run one of these models with quartz plus albite going to quartz plus kaolinite, and you typically we make plots of concentration of whatever's dissolving. So this concentration of albite, I'm sorry, concentration on this axis and depth on this axis. If life was really simple, we could just plot concentrations, but we often normalize it, because if you remove one element or one mineral, the other mineral will become more concentrated. So most of my plots will be this what's called a mass transfer coefficient. It's a normalized concentration, and we normalize it using the concentration of albite in the original parent rock and some immobile element or immobile mineral composite or concentration. So tau, or the mass transfer coefficient, is equal to 0 when you have your parent concentration of albite, and it's equal to -1 when it's 100% depleted. So if you allow rain to fall on a rock that started out over here, where everything was plotted at tau equals 0, so parent composition, albite dissolves away, and you get what's called a reaction front that moves downward with time. So this is a system that's not eroding. This is the albite concentration with time. And what happens is you start out with an incompletely developed front, and then it becomes 100% depleted, and then it moves downward with time. This is where we just allowed solute transport by diffusion. And in the next slide that will come up. I'll show you what it looks like with advection. But first, I wanted to just emphasize that this is the only place in the profile where the feldspar is dissolving. This is what we call the reaction front. It's the depth interval across which the reaction occurs. And I usually give it the symbol to just small l. You can think about it if you want. If this was all kaolinite and this is where the albite was, the reaction front can be very narrow. And you've probably seen these, they can be very narrow in some cases. If you allow there to be advection in your system, so you have water flowing through this system, what you tend to see with the models is the reaction front gets wider. So this is really the same thing. You know, here's that reaction front developing and moving downward. The reaction front is wider, and then the depth of the entire reaction for some given time is also greater. So it turns out that this reaction front, we see these all around us, and they have a lot of information, and these are patterns that we can start to learn to read really easily. It turns out that at least in the models, the reaction front thickness is a function of how much advection goes through the system divided by the rate constant. So it's the ratio of transport to reaction. And the depth you can think of as the advection velocity times the solubility. So that's the total amount that can be removed per packet of fluid divided by however much albite there was in the system. So there's a lot of information there. The depth is telling you something about sort of the solubility removal of material. And then this reaction front tells you about the ratio of transport and reaction. So that was all without erosion. That was a system where it was deepening with time. And I started out telling you that a lot of systems kind of move to a steady state. So what if you run the models so you impose an erosion rate equal to this weathering advance rate, or this weathering advance rate here? Well, then you can get these sort of, these steady state models, and you still see a reaction front. So here's a reaction front. This is the case or a very, very low erosion rate. If you have a very high erosion rate, you can actually end up with albite that actually makes it to the surface. So just to recoup kind of what I was saying, 0 is parent composition, -1 means 100%, all the albite is gone. So a reaction front that looks like this, some of the albite is making it to the land surface. And so basically what we're saying is very slow erosion rates, none of, the albite goes through here so slowly that it dissolves away before it reaches the land surface. So that would be like Brazil or places around here in cases. And then mountaintops where the erosion is faster, the albite goes through the weathering zone so quickly that it makes it to the land surface. So if you get nothing else out of the talk than this, I think this is a really useful thing. If you're walking around a piece of the planet where there's albite right at the land surface, that means that it's moving through that weathering zone fast enough that it can't dissolve away. Whereas many parts of the sort of temperate climates and tropical climates where the erosion isn't really super high, the albite is gone well into the subsurface. So people talk about the chemical depletion fraction, or theta, and it's how much is dissolved away versus how much is eroded away. So the chemical depletion fraction is just related to this idea. You either lose all the albite in the subsurface or you have some of it that makes it up to the top because the erosion rate is so fast. Well, you can play all sorts of games with these. You can put fractures into the system. And here the blue is unweathered. The red brick colored is weathered. The colors in between, there's still some albite in here dissolving. These are fractures. And what you see is, depending on how you set up the model, but what you see is when you increase your fracture density, you actually get deeper weathering and you get wider reaction fronts. So these are the kind of patterns that the models tell us should be out there. And now I'm going to sort of talk to you about some different systems, and I think you'll see some of these patterns as I go through. And this just kind of summarizes what I was just talking about. There are systems where the reaction front is very narrow, where the reaction front is wide, where the regolith thickness is very large, and then where some places where the regolith is not as thick. Okay, so let's go to shale hills. Let's talk about a real system and see what this looks like. This is up in the hills, just half an hour from here. So it's in central Pennsylvania. It's a very small 0.1 kilometer squared watershed, and it's developed almost completely on Rose Hill Shale. It is completely on Rose Hill Shale. There's a little bit of layering of carbonate out towards the outlet. And it's mostly clays, illite, and chlorite, a lot of quartz, a little tiny bit of plagioclase and pyrite and carbonate. We've measured its erosion rate. It's eroding at 20 meters per million years. And we've measured all sorts of things about it with all sorts of people. So we have a lot of data that we can think about how it works. We've got boreholes, and I'm going to talk about a borehole in the northern ridge. This is north in this direction, and then one on the southern ridge here. And I'm going to show you tau plots. So here's some tau plots. This is the tau plot for pyrite. Here's the parent composition of sulfur. So this is when all the pyrite is in the rock. Then it all disappears, and then there's no pyrite left. Same for carbonate. There's a little bit of carbonate, and then it all disappears, and then there's no carbonate. And then the slow dissolving chlorite comes out at, this is down at like 22 meters or so. Here's the parent composition. Here's the chlorite slowly dissolving away. And this is the magnesium, and this is the iron in the chlorite. So this is the reaction front for pyrite. This is the reaction front for carbonate. They're completely developed. They're fast reacting. So they completely disappear before they've moved all the way through the weathering zone. Chlorite clays are less reactive. So it makes it all the way is exhumed at the surface because it's not as reactive a phase. Just showing this schematically, this is for the southern borehole, but it's pretty much the same thing. The pyrite and the carbonate dissolve and disappear at depth, and then the chlorite makes it all the way to the surface because it's a slow reacting phase. So here's one of the plots that I showed you. This was for albite plus quartz, but I've told you that the reason I do these models really is to understand patterns. But you can see that if the ratio of erosion to chemical weathering is such that the mineral doesn't make it all the way to the surface, you get patterns that look like this. That's like this one, versus if the clay dissolves very, very slowly compared to how fast it's moving through the weathering zone, you're going to get patterns like this, reaction fronts like that. So I threw this in here because it's going to come up later in the talk, assuming I don't go too slow, which I'm already going too slow. We can look at the data as a function of depth and relate the different weathering reactions to porosity. And the reason I want to do that is because at the end of the talk, when I show you the geophysics, seismic velocities, they can't tell chloride versus plagioclase. I mean, they can respond to the density of it, but what they're really responding to is porosity. So I just wanted to show you that this shale has a very low porosity at depth. And then as these weathering reactions occur, little tiny bit of porosity grows from plagioclase dissolution. Most of the porosity that grows in the rock from weathering is this chlorite weathering that I was showing in the preceding slides. And the other thing I wanted to point out is that the pores in the shale are very small. The pore throats are like 20 nanometers at most. So it's a very, very tight rock. But now I'm going to talk mostly about pyrite oxidation. And I want to do kind of a deep dive about pyrite just to kind of show you how you can put this whole thing together. Here's the pyrite reaction front, the tau plot that I've already showed you. And some people don't believe when you show them a plot like this and say this is a reaction front, that it really is a reaction front. So we looked, and we do see pyrite down here. In fact, we see pyrite framboids. Here they are in 10 micron. This is an SEM micrograph. And then when you look up here, it's very cool. You still see framboids, but they are completely changed into iron oxide. So pyrite framboids down here, iron oxide framboids up there. So this is a reaction front where the pyrite's oxidizing away. And it happens right above the water table. Here's where the water is going up and down. And this is rain, just shows you the amount of rain coming in. And the oxidation is happening in the capillary zone right above that water table fluctuation. So if we look at this reaction front now and think about what we think is happening there, we have shale coming up that has pyrite, and the shale is fractured. And in fact, we know for at least one of the boreholes I'm going to show you data for that the average fracture spacing that we can see by televiewer, something like 12 centimeters. And so what we think is happening is the pyrite's coming in, or the shale's coming in, and oxygenated water is making it to these fractures, and that as the 12 centimeter piece moves up and through the system, it becomes more and more oxidized. And so I'm just going to show you how that can work. I can't prove to you that this is how it happens, but I'm going to show you how that works and that it makes sense from everything that we can measure. So the amount of time that any given one of these pieces spends in this reaction front is 1 meter divided by the erosion rate, 20 meters per million years. So it's about 50,000 years. So that means that the oxidation has to happen over 6 centimeters, because it's happening from both directions, in 50,000 years. And so using just a real simple diffusion model, we can calculate an effective diffusivity in this matrix, in this shale matrix of 10 to the minus 12 meters squared per second, which is a reasonable number for shales. And what we tried to do is then look and see, what else can we learn about how this oxidation happens? And we saw that although most of the oxidation occurs in this reaction front, this 1 meter thick reaction front, in at least one of our boreholes that we got logged core, we saw some fractures deeper where we see some oxidation. So if we look at one of these deeper zones and we look at a class that was returned, we actually can see one of these pieces that we think is oxidizing. And so here's the fracture surface, and all the way along when we probe it, we see oxidized pyrite until we get to the very furthest part, the 6 centimeters away from the fracture, where the pyrite is still present. And you can see these over here. So here's the completely oxidized little pyrite grains. And then here's partially oxidized pyrite grains, showing you that the reaction front is like a millimeter in thickness. So here's the reaction front at this scale. And here's it's like a millimeter in thickness. The oxidation has advanced 6 centimeters, and the reaction front is like a millimeter. And then you can go down even to a finer scale. Here's a TEM micrograph looking across. This is a cross section through one of these pyrite grains. Here's pyrite, and then here's iron oxides. And if you look at it at this scale, 200 nanometer scale here, it first changes to ferrihydrite, then it changes to goethite, and then it changes back to ferrihydrite with a lot of porosity in it. And so we don't understand why all those mineralogical transformations occur, but this is where the oxygen is actually diffusing in, and sulfur species in H+ has to be diffusing out. Ferrihydrite is known to form at near neutral pH, and so we think that the H+ is neutralized by the shale, which is on the outside here, and we never see any sulfur phases precipitating. So we think that the diffusion of sulfur species must be fast, because we never see it hanging around. We either see the iron sulfide pyrite or we see iron oxide, and the sulfur is gone. So we've inferred again from this that oxygen diffusion limits the rate. So if we put this together across the whole scale, this is the first time in my career that I was able to do this. Here's the pyrite oxidation front shown at the borehole scale. I started out, so this is meters. And then at the sort of clast or fracture scale, here it is where it's sort of 6 centimeters inboard with a millimeter reaction front. And then here is that TEM scale that I was showing you, you know, how thin that front actually is at an atomic scale. So again, if we use that 50 kiloyear time constant, the rate has to be, these pyrite grains are 5 microns. So there's a 5 micron pyrite in 50 kiloyears. You get a rate that's about 10 to the minus 14 moles per meter squared per second. And we can compare this to laboratory rates. This is a complicated plot. This is log rate versus atmospheric oxygen done at different pH values. And if you look at our field rate, which was down here at 10 to the minus 14, and then we look at the, we assume that we have oxygen that's something like 10 to the minus 1, like 10% of atmospheric. The lab rate should be here where we're 4 orders of magnitude slower. And that's actually very consistent with that diffusivity that I mentioned to you. So what I tried to show here is that no matter what scale you look at this, you can make a model that shows how this system is working and how this oxidation is happening. So the observations are going from like 100 meter scale to 0.1 nanometer, and they are consistent, at least in this sort of, you know, numerical and thought experiment way of thinking about the system. We think that oxygen's brought to the depths of tens of meters in the groundwater to the fracture. It diffuses inward with a diffusivity which is like 3 orders of magnitude slower than aqueous diffusion. And we think it oxidizes abiotically. I didn't emphasize this, but I told you that the pore throats in the shale are like 10 to 20 nanometers, and that is much smaller than bacteria. And so if there are iron or sulfur oxidizing bacteria in the system, and we think there are because we've worked and analyzed them, they can only be living in the fractures, and yet the oxidation is happening in the matrix. So the rate of oxidation is abiotic, and we think it's paced by the erosion. It is slow because of the erosion. It is actually, you know, dictated by how fast the clast moves up through the system. All right, so if that's true, we should be able to see the oxidation rates much faster in more quickly eroding systems. And so we did, we looked across some shales eroding, weathering and eroding at different rates. So here's Shale Hills. And then we went to another CZO in Eel River, Northern California. And then we worked with Josh West, who had samples from Taiwan. And they're all shales and they're all weathering. And here's the data for the different systems: Shale Hills, California, and Taiwan. And it's not a perfect experiment. The erosion rate is 100 times faster in Taiwan, and it's 10 times faster in California. But the temperature changes to some extent, and and then the precipitation is also faster in Taiwan. But by far the biggest change is in the erosion rate. And so we asked the question, first of all, how much sulfate is being released in these watersheds? Because that tells you what the erosion rate most direct, or the weathering rate of the pyrite is most directly. And so when you plot this, when you plot the weathering flux of sulfur out of each of these 3 systems versus the erosion rate, and we had to do the weathering flux divided by how much sulfur there was in the bedrock, because there was slightly different pyrite contents, you do see that the sulfate release rate increases with the erosion rate. So it does seem like it is being paced by the erosion rate, which makes sense based on some of those models that I showed you earlier with the reactor transport models. And we looked and we saw almost identical patterns. So here is Pennsylvania. Here's the unweathered pyrite framboids. Here's the weathered pyrite framboids. Here's California. Here's the unweathered pyrite framboids. Here's the weathered pyrite. I'm sorry, I might be saying this wrong. Iron oxide framboids, iron oxide framboids. Here's the unweathered pyrite framboids in Taiwan. Here's the weathered iron oxide framboids. And when we look at the tau plots, it looks just like we were predicting with our models. So here's the pyrite and the carbonate, it has enough time to totally dissolve away. Here's the pyrite and the carbonate, totally enough time to dissolve away in California. This is Shale Hills, pyrite and carbonate. We don't have complete control here in this Taiwanese system, but we know that the pyrite is gone by the land surface. So in effect, the erosion rate increases by 100-fold, but the pyrite and carbonate are still so reactive that they're still making patterns that look like this, making reaction fronts that look like this. On the other hand, if you look at the chlorite, which I told you at Shale Hills was not a fast enough reactor that it disappeared, but it actually was being exhumed at the surface, you can see that you're moving towards less and less weathering of that chlorite. So you're sort of moving in this direction in these systems. So this experiment really, I think, tells us that these models, even though this is albite plus quartz and these are shales, these models are telling us something really powerful about how these systems operate. How does it actually weather faster? Just because it's eroding faster, how does it actually weather faster? Well, I think it's actually, there is a higher density of fracturing that must be accompanying these faster erosion rates. So here's Taiwan, California, and Pennsylvania. If we look at the spacing of microfractures, we see microfractures spaced at about 5 centimeters. As I've mentioned, very small number of fractures at depth in the Pennsylvania shale. But we see lots and lots of fractures in the California system. Spacing is more like millimeters, and we see lots and lots of fractures in the Taiwanese system. So in fact, if we measure the porosity versus depth in each of these, Pennsylvania, California, Taiwan, there's a lot more porosity in the fast eroding system. And the brown here is the fracture or microfracture porosity that's developing in these fast eroding systems. So the microfractures in the fast eroding shales may actually explain mechanistically how the shales weather faster in these high eroding systems. Okay, so let's now go 1D to 2D to 3D, and I'm just going to show you some of this seismic work that we've done to try to start to give you an idea what it looks like across the landscape. Well, why did we go to the geophysics? Well, because the only way we as geochemists can tell what's going on in the subsurface is from boreholes. So if we want to know what the reaction fronts look like in the subsurface sort of in 3D, we have to look at different boreholes. And so I thought I'd just start there. I showed you that pyrite was oxidized all the way down to 23 meters up here in our watershed. Here, it's only oxidized to about 16 meters. And then under the valley, it's only oxidized down to about 6 meters. So you can see that the depth to where you start to find pyrite is shallowing as you're moving out of the watershed. So we thought that if we did seismic, we might be able to see some of these reactions. And so we did refraction seismic surveys, and we also did a very closely spaced dense array in here, but I'm just going to show you one transect that goes from the outlet to the south borehole. And this is what the data look like. This is a fast inversion showing P wave velocities in 2D, contoured from blue. This is the fast, the 4,500 kilometers per second, 4,500 meters per second, we think is the unweathered shale, to slow, and the weathered shale is plotting in the warmer colors. And the contours here are the P wave velocities. And we were able to look at our borehole data and then try to overlay it on this to try to see if we can use the seismic, the P wave velocities, to tell where weathering is occurring and the extent of weathering. So the point where pyrite starts oxidizing down here is deeper than we have control from our P wave data. But the point where the chlorite starts oxidizing and weathering is right here. Up here in the ridge, the pyrite and chlorite start right about here. And so what we noticed is that the chlorite dissolution starts under the valley at the 2,700 meters per second P wave velocity. And it also, the chlorite starts dissolving under the ridge at the same velocity, P wave velocity. And this kind of makes sense to us because, as I showed you earlier, the weathering reaction that creates the most porosity is the chlorite reaction. So if we were going to see a reaction with the seismicity, the seismic waves, this would probably be the one that we would see. Now, we see that the seismic velocities don't get back to what we think are the sort of values unweathered, even below this pyrite oxidation front. And so I'll just remind you that down here is where we saw a small number of fractures where we saw oxidation around the fractures. And so we're hypothesizing that there is pyrite oxidation and carbonate dissolution around fractures down here that are kind of being averaged out by the seismic velocities, and that's why you see it down here. There's also evidence down here that we're not reaching unweathered material, but we know from the borehole material that there's actually some carbonate dissolution and pyrite oxidation going on down here as well. All right, so what we wanted to do was be able to go from the P wave velocities to weathering reactions. So we tried to do this by using a rock physics model, which took bedrock chemistry and information from borehole logging, and then use that model to try to predict porosity fracture profiles for comparison. And so we did this with Gary Mavko at Stanford before he retired. And basically, with sonic logs down the borehole in the outlet of the watershed, we were able to measure P wave velocities and S wave velocities. And then in a plot of the P wave velocity versus the ratio of P to S wave velocity, here are the data for that borehole. And they're color coded by the depth. So at the deepest depths where you're down below pyrite oxidation at 30 meters, you plot on this diagram, which I'm going to explain in a second, plot over here. And then as you go to the shallower, more weathered material, you're plotting in these lighter colors. So how is this diagram? This is a diagram that comes from the rock physics model. These are the minerals that make up this shale. So quartz, anchorite, a little bit of anchorite, chlorite, illite, and calcite. And from the bulk moduli of those minerals, we know where they would plot on this diagram. And if you put them into the average mineral mix of the rock, this is where your rock should plot. So you should have, if there's no porosity in the rock, this is where it should plot on this P wave diagram. If there's porosity and it's 1% and it's water-filled porosity, it would plot here. And if it's 2% porosity, it would plot up here. And so very consistently, the data plot at about a little bit more than 2% porosity, which we've measured in the rocks at downhole, water-filled. And then as they shallow in this borehole, they stay roughly constant in porosity for a while, and they move towards a gas. The only way we could explain the data is by a gas-filled model. So we discovered from this that even below the water table, there actually is a fair amount of gas in the water, in the shale, much deeper below the water table. And it's the only way that we can explain the data. So with that, we could then take the transect that I showed you. This is contoured for the P wave velocities, and we can change it into porosity. So we can take this and change it into porosity, as long as we assume either gas filled or water filled or some, ratio of gas to water. So this is, gosh, I forgot what it is now. I think this is the gas filled model. And these are now contoured in porosity. So what you're seeing is taking these P wave velocities, this rock physics model, and then plotting it as porosity. And so what I like to think of is that to great extent, this is where the chlorite weathering begins. And most of this change here is in porosity is simply from that chloride dissolution, which creates porosity in the rock. It's not till you get to the shallowest part that illite starts dissolving and the rock actually starts fracturing apart. And that's when you get other increases in porosity. Now, why do we think the P wave velocities are telling us about the porosity and not the fractures? Well, one of the reasons, well, first of all, I think you could probably make a fracture model that explained this just as well. So it's non-unique to say that the seismic transect is explained in this way by the porosity. You could make a fracture model, but what we see is that the fracture density, this is from the televiewers in the borehole down here, and this is the fracture density in the borehole up here. The fracture densities don't seem to correlate with what we see from the seismic, whereas the porosities do. And if you go to our paper that explains this in much more detail, you can look at a lot of the different data from across the watershed and decide for yourself if you think that's right. But it looks to us like this seismic data is showing us, it is mapping out what this oxidation front looks like well, not the oxidation front. What we're seeing is the chlorite reaction front. We didn't get enough depth to see the oxidation front from the pyrite, which I emphasized earlier in the talk. Okay, so let me just leave you with a little couple cartoons and thinking of what I think happens here. These are some of our models, Marina Lebdev and my models. This is, albite plus quartz going to kaolinite plus quartz. Here's a hill that we've allowed to weather for a long period of time. Red means all the albite is dissolved away. This is the starting rock. The reaction front is right here. And now we're doing this with flow, and we've allowed the porosity change that occurs because of the reaction to change the flow lines. And so what is very common with these models, we had to make an assumption about how the permeability changes as a function of the porosity. But what you see is these reaction fronts typically change porosity, which changes permeability, which also changes flow. And so I think these reaction fronts may act almost like valves that affect the flow lines. And that if we could map them and understand them, we could say something about water flow. And if you think way back in the beginning of my talk, then maybe the subsurface wouldn't be so much of a black box. So here's what I showed you over and over again for shale hills in 1D. Here it is in 2D. And what we know happens at shale hills, we get like 1 meter per year of water. 90% of it goes out in the upper part where this illite reaction is occurring. Only a very small amount of the water makes it down as far as the pyrite and carbonate reaction fronts, and then that water goes out. And I think that if you look at my reaction fronts here, I think that you could convince yourself that part of the reason that you're seeing these different flows is because of the changing in porosity of these weathering reactions that affects the permeability. So now back to shale hills. This is that transect I showed you, and this is the kind of the end. This is water comes in, oxygen enriched interflow goes out through the upper part. And that's a valve that really is probably related to the illite weathering at the top. Then some infiltration makes it all the way down to where the pyrite oxidizes. Then you get some groundwater that moves along that front, that pyrite oxidation front. But some of it actually goes deeper because we know it's down there in those deeper fractures where we saw the halos of oxidation. And putting it all together, this is from that paper, We know we've also measured downhole with logged heat pulse flow meters. So there's a upward flow down here at this borehole and downward flow here. And that change from downward to upward flow is right about where that pyrite oxidation front starts. And so I think that what you're seeing here is really, in some ways, for the first time, being able to put together the system that's combining water flow and weathering, and then, you know, what it looks like with some of these geophysical tools as well. So that's it. I hope you hung on, because there's kind of a lot of stuff that I threw at you. Here's what you can go home with if you don't think about this stuff as much as I do. Field rates become increasingly slower with larger spatial scale, at least partly because new steps become rate limiting. The erosion rate became rate limiting, and that was the pacemaker, I think, with that pyrite oxidation. The reaction front of what we think is abiotic oxidation and buried shale defines a subsurface landscape, which is influenced by the flux of oxidants, acids, and waters from the land surface. And here's like one way to think about it. Here's fractured unoxidized rock, more fractured oxidized rock, and then soil at the surface. Here's that front that we're trying to now think about in 3D, and it kind of looks something like this. And we're starting to understand the geomorphology of these subsurface landscapes. And I think these reaction fronts are important. They may control something of the permeability architecture. And the more we can understand them using whatever tool we can, I think the more we'll be able to understand about the groundwater resource, which is obviously important. So thank you for the opportunity to talk about all of this work.
Well, thank you very much, Sue. We'll give you a virtual applause. I guess that's the thing I miss most, really, about being in person, but